Okay, let's start with the session number 11. Today I'll be introducing the rapids along with Dask and show some of the libraries and APIs that can be utilized using Nvidia Rapids open source project. And apart from that, I'll show some comparisons using like a comparison between Pandas and rapids for a couple of commonly used functions in Pandas. Yeah. So coming to the data processing pipelines, this is how it has evolved over time. So initially, these were the number of modules or tasks that was being done in the data processing pipeline. Like the data was being queried from the Hadoop file system, and later it was being saved onto the disk. Again, for ETL jobs, it was again read from the disk, and it was again preserved on the disk once the ETL jobs are done. And for ML training, again, the loading operations were being done before starting the training. So this was a common procedure before, and like all these operations, like it was not possible initially to load into the RAM itself and persist till all these procedures get completed. But later on, once Spark was introduced, this in-memory processing was also like the starting point for data processing pipelines. So here you can see once you read the data, you can query to the ETL jobs and as well as train the models without any write operations, as you can see at the top. So that was the difference. And apart from that, Spark was also able to completely utilize the virtual or your local machines resources, and it was able to scale out depending upon the load. And anyways, the Spark, it just utilizes the CPU resources. So once the GPU was also introduced, so this is how the whole data processing pipeline got transformed. So here you can see almost the same as the first box, but the only difference is the GPU. In the first box, everything was happening on CPU, and here it is happening on GPU. So you can see the kind of improvement from the first box to the third box. And rapids, you can compare this with the Spark itself. So here Spark is using CPU resources and rapids is using GPU resources. So that's why you can see the size of these boxes have got reduced to a significant extent. And that's the only difference. So rapids is able to completely utilize the GPU resources and try to do this extract, transform, and load operations, and as well as training of machine learning models. And one more addition in rapids is it uses Arrow. So Arrow is a open source project. It is a in-memory columnar format to store the data. So if you have heard of Google's protocol buffers and flat buffers, so that is being used like if you are if you train a model in TensorFlow and store it, you can see the file system. You'll find a file with the format ending with PB. So that that file is known as a protocol buffers file. So that is a file in which the model usually gets stored. So we can compare that protocol buffers with Arrow. So protocol buffers will usually use some common algorithms as well as serialization algorithms to store your model into the hardware in the format in which it understands. So similarly, Arrow is also one such format. So the only difference in with protocol buffers and Arrow is, so Arrow, the way you store the data and the way you read the data, it is the same. The format in which the data is stored in the hardware is the same as what is being read from the disk. So there is no change. But in protocol buffers, you try to deserialize or serialize depending upon whether you're writing or reading the particular model file from the disk. So that is the only difference between protocol buffers format and rapids. So here the operations are very fast in rapids because there is no deserialization that is being done when you're trying to read the data files from the disk. So coming here, using the CPU workflow compared to the previous slide, you can see the data scientist spends most of the time in ETL jobs as opposed to training the models, because here you can see we do lots of additions while doing the ETL jobs, and something if we have forgot before running the ETL job, then we have to wait a lot of time after adding the new feature as well to get it completed. So here you can see in a day using a CPU workflow, the person is having lots of coffees and degrading his health as well. And he's also waiting more time to get these jobs completed. And once he starts using the GPU workflows, you can see the difference between these two diagrams. The dataset download time is almost the same, but apart from that, all these boxes, the size got reduced from CPU to GPU. So you configure the ETL workflow and start the ETL job. And suppose if you have forgotten to add a feature, here you can see you try to add it and again start the ETL procedure, restart the ETL procedure. So even after several iterations, you are able to complete the ETL procedure by this time, which was not happening with CPU even after the complete day. And after that, you train the model, validate it, test it, and experiment with different hyperparameters optimizations, different new columns, adding new features into the data frame. All those things. Any questions still?
Nope. I like the image of getting a coffee and then that you forgot a feature, you have to add it or you wait again. I think everyone can relate to that.
Yeah. Okay, so coming to Rapids, so this is Nvidia's open source set of libraries and APIs. So Rapids, it is not just limited to the data processing. So here, right side, you can see the diagram. So QDF is similar to Pandas dataframes, which is mostly concentrated to analytics. But apart from that, Rapids APIs also focus on machine learning. It has like algorithms for XGBoost, gradient boosting, random forest. So those kind of algorithms as well, which can be utilized to train on the GPUs. And even for graph analytics, there is a set of libraries that is a cuGraph. And the rest of these, you anyways know, PyTorch, TensorFlow, MXNet, the deep learning based libraries. So apart from that, even this Rapids provides visualization libraries combined with Plotly and PyVis. You can see this CUX filter. So all the visualizations for huge data frames is also provided with Rapids with appropriate APIs and libraries. So what is the benefit of using Rapids? We'll see some of the high level benefits of it. So the first one is scaling out on GPUs. So as I mentioned before, obviously all the data processing jobs, it would like speeden up using GPUs instead of just the CPUs. And apart from that, we can use from the previous diagram. So here you can see DASK as well in between these two. So DASK is actually trying to scale in and scale out all these operations. So by the way, from CPU, you're anyways using GPUs, but suppose you have multiple GPUs or you're working on a remote cluster with lots of virtual CPUs as well as GPU in combination. So in those cases, task is used to scale out all these particular jobs to all those remote nodes in that particular cluster, so that you are effectively using all the resources that are available to you. It might be CPU as well as GPU or combination of both. So dask is coming into picture for scaling for all the resources that are available. Rapids just scales with GPUs. There's the only difference. So the reduced training time, so we can improve the model accuracy as well as reduce the training time. So that can be possible using these Rapids APIs, and it is open source. It is supported by Nvidia, as well as yeah, it relies on a number of open source projects, as I mentioned before. That is one of it is Apache Arrow, and the other one is Numba. So Numba is a open source Python compiler. So you can fasten up your Python functions using this Numba's JIT compiler decorator. If you just embed this particular Numba's JIT decorator on a particular Python function, then this Numba Python compiler will try to convert your Python code into low-level C or C++ code, and later into machine code on runtime, and tries to speeden up the training or inference, whichever the function is pertaining to. So all these are open source libraries which are being again used by another open source project, that is Rapids. So in the right side diagram, you can see what is the time that is being utilized by different kinds of resources. With the CPU nodes, how much time is being utilized for data processing, feature engineering, data conversion, and ML training. And with the DGX box by Nvidia, you can see how much the time is being utilized by using the GPU resources. Yeah, so this discussion is just limited to CodeF because the machine learning as well as graph analytics, we don't have the requirement right now. The requirement is for data processing using the data frames. So this discussion is just limited to CodeF. So here, this is almost a similar diagram as you saw in the previous slide. So CodeF is like a single GPU data frame library, which is built on Apache Arrow columnar memory format. So this CodeF APIs, they almost provide everything what was being provided by Pandas APIs. So you can do the operations like loading, joining, aggregating, filtering, and you can manipulate the data. All the data wrangling operations can be done using CodeF. So task CodeF will come into picture when you have your data file sizes greater than your GPU memory, single GPU memory. So at that time, if you are not able to load your data onto a single GPU, then you try to have multiple GPUs and try to scale it with the task combined with the CodeF. So there are libraries and APIs provided by Rapids to do that as well, so that you can use the multiple GPUs in a single machine or many GPU machines in a remote cluster. So that option is available. So depending upon the data file sizes, we are supposed to choose which one to use. So we have the option to use CPU. If the data file size is very large, then we can just use a single GPU and try to do the operations using CodeF. And if the data file size is very large than the single GPU memory, then we can go with the DASK in combination with CodeF.
I have one question, Shreyas. Maybe the question is, oh, I think the question is a bit too fast. I think I saw something on the next slide about the syntax.
Okay.
So never mind.
Yeah, go ahead. Go ahead.
Yeah, question was, so if we're gonna use the QDF, what would the syntax be like? Would it be quite similar to Pandas and Dask, or would it be different? But I think that's coming up next.
Yeah. Yeah, the syntax is almost the same. I didn't find any difference as such, but there is very good documentation as well. Whenever you find it difficult, but everything is almost same as Pandas itself, because this is these APIs and libraries are built by referencing the Pandas APIs functionalities itself. And I guess I mentioned before last week, I guess, that all the APIs that Pandas provides are not yet completely supported on CodeF. So they do support based on its like usability on GPUs, and like if it is taking, if those operations are taking more time on GPU compared to CPU, obviously there is no point of having those kind of APIs. So so obviously there is a limitation over here. Apart from that, we can use these GPU data frames from like a NumPy arrays or Pandas data frames, or even PyArrow tables. Like last week, I guess, when Stephen, when you were showing the Jupyter notebook for NLP v3's transformers, I noticed the data file format was a bit different. I forgot the format name. That one was something I was searching for. Feather, yeah, got it. Feather file format. Yeah, so that feather file format is the format of PyArrow itself. So PyArrow uses its like only defined IPC, like a PyArrow IPC format. So if you store your data frames or tables in this feather format, then it would be using PyArrow's serialization libraries, which would like use the in-memory columnar format to store the data as well as to load the data. So if we Numbers JIT compiler as well with these particular data processing operations with custom user defined functions. So all these advantages we can take using CodeF. Comparing Pandas and CodeF, so these are some of the like benchmarks for commonly used operations. So for string operations, you can see when you lower the case, what is the time that is being taken using Pandas, and for with CodeF to find like a particular regex format. So you can see all these benchmarks. It is very less using the CodeF. And for IO acceleration, the input output, you can see when you read the data, this data is about 2 GB. So when you want to load it with Pandas CPU, you can see it is taking 30 seconds, whereas using CodeF, it is just taking 2 seconds. And this one, these numbers are with a custom data set, a time series data set. So I was just looking out for data file sizes like a bit more. So I was experimenting with around 5 GB of data. So here these are the like a time taken by Pandas as well as CodeF for these different operations. The Parquet format, reading the Parquet format files, group by, and rolling mean aggregations. So in all of these, you can see almost there is more than 50 times acceleration compared to the CPU numbers. Here. So I also try to use Dask CodeF for these operations for this data file, but it was taking more time. it was taking more time than Pandas. That was happening because the data file size is very less, and it was not meant to be to use DASK in combination with ODF for the data file size that I was working on. So I was working on a single GPU machine, which was not supposed to be for DASK ODF. So that's why it was taking more time than Pandas. So maybe if I try to use with multi-GPU systems, it will try to scale out a bit better. And some of the limitations of RAPIDS ODF is it requires approximately 4 times more GPU memory than the data file size. So this was almost an year ago. This was a limitation, but even now I don't think this has been addressed properly. When I was benchmarking for the custom data set as well, while computations, it was taking more GPU memory than the data file size. So this is one of the limitation. And the second one is user-defined functions are limited to Boolean and numeric data types. So on data frames, we just try to use the apply function or map function with in combination with the lambda functions, right? So to do the data manipulations. So in those cases, it is just limited to Boolean or numeric data types. So if we are doing some string operations with this UDFs, then it doesn't work. They are trying to add these functionalities as well in the future releases. And it doesn't support all arithmetic operations such as bitwise operations. And QDF currently implements only a subset of Pandas APIs, as I mentioned before. And apart from that, not all DASK data frames of data frame operations work with QDF. Yeah, so these are some of the limitations of QDF. So depending upon the requirement, we are supposed to wisely choose which one is better for our use case, considering these limitations. Yeah, thank you. Any questions?
Nice, thanks for the presentation. I do have one small question. So on the previous slide, you mentioned that the RAPIDS and the QDF doesn't support string transformations, right?
Yeah, for now.
Yeah, so what would there be an alternative that we can use? Or would it just be like a regular Pandas data frame, for example?
No, for strings, like if we are using user-defined functions, if we are defining some custom functions and trying to manipulate these strings, then it is not going to work out. So we might supposed to wait for those operations for future releases. So they are supposed to, they are working on it. They will do those in the future releases. So till then, we are supposed to use Pandas itself.
Yeah. Okay. Cool. Thanks.
Any more questions?